Welcome to the course on FPGA-based signal processing systems. We'll continue with the digital circuits modeling and the test bench, which we had seen in the previous lecture. So, the AND gate example, which we had looked into, the test bench module, which is called inside a test bench. So, if, in the test bench, we had the module and the test bench name. That is also a module name, and then the inputs and outputs are declared and initialized, and then the module is instantiated. After instantiating the module, we give the stimulus, add the stimulus to the module, and then the stimulus contains the different input combinations A and B and the Y. After giving them, and we monitor that using the $monitor statement in the waveform editor. So, the waveform editor which is shown over here, the piece of that output, here we could see the changes, the B change and the A input change. So, the expanded version, I would in the example would show you that 100 time units, which changes this, where the input is asserted to 1 is shown over here, A. This is A, and in B the input is asserted at this point. So, when A is 0, B is 1, and the AND gate gives 0 at this point from here to here, this point, and then when A is 1 and again B is changed to 0, if you remember 1 0. So, this is 0 0 part, and then here 0 1 and 1 0 in this portion, 1 and 0, this is gives output is 0, and here also 0, and this is 0 for while her 100 time units, and then 100 time units we had also kept it 0, 1 0 0 1 1 0, and then here it's both of them. This is already 1, A is 1 and B is asserted to 1, asserted here 1 and 1, so give the output 1. So, this is how the waveform editor looks like. You can see the time variations where we are changing the input also. So, you are seeing, because A and B are single bit, you see the waveform 1 bit, how the 1 bit digital 0 and 1 is changing here. So, this is the output of the waveform editor, which is monitored, and if you use the $monitor in the console, TCL console, there in the design suits or the Vivado environment or in the simulator, the time resolution here it's taken as picoseconds, or it can be in nanoseconds as well. So, where input is A 0 and B is 0, the output is Y. So, we have given the $monitor statement, if we recall, within the quote Y percentage B, Y equal to percentage B, and then A equal to percentage B and B equal to percentage B. The decimal one, it is 0 and 1, so there is no difference here. Percentage D, if you give, it is going to be decimal number. If it is percentage B, it is going to be a binary number displayed. Y, A and B, and we have given the comma separated also. So, the output is plotted first, and A is 0, B 1, and A 1 and B 0, the corresponding output is 0, 1 1, and the output is 1. So, you can have the statements or the inputs and outputs printed as well. You can see the new line, the use of new line in the $monitor statement. So, which the first statement, and then comes to the next statement for printing, the new lines also can be issued. So, this is the output of this AND gate module which we had done, and its test bench giving the output in the Vivado, Xilinx Vivado. And if we consider the next example, so similarly this OR gate, and I quickly go through this OR gate one. We had module and N module, OR gate structural module name, input A B, output Y, and you are instantiating OR, and gate 1 is G1 gate name, YAB the output, and followed by these inputs. This is a built-in OR gate. So, the OR is a built-in OR gate number. So, this cannot be changed. That is one. The OR, the gate 1 G1 is the optional name. And in the data flow modeling, so we have this data flow model of OR gate module, OR gate data flow, input, and we use the assign statement and the ARB. So, this is a bitwise, and in the behavioral modeling, similarly, the behavioral module and N module, we had this behavioral module input A B and the output reg. Remember, always at the rate A or B, Y equal to A or B. So, always at the rate A or B. So this is for the always block and test bench. Now coming to the test bench for the gate. So again the structural model is considered. It can be of any data flow model or the behavioral description as well. So module have the module name. Module name is here. The test bench module name is underscore gate and test. This is of our choice, and that doesn't take any input. Okay, so within the bracket, if you see, it's a Verilog code, but there is no input as such in the to be written in the within the bracket. So now the inputs needs to be specified separately. That should be declared as in the case of AND gate A and B, and the output is Y wire Y. Also the instantiating that OR gate module. So OR gate structural model, this can be of any of this data flow or the behavioral model as well. So UUT, that is unit under test, this is port name and this is local expression AB, and this dot B, and this corresponds to the local expression, and instantiating the that OR gate module here in the test bench. So once this module is instantiated, the input and outputs are specified, module is instantiated, the next step is that give the initialization or initialize the inputs A equal to 0, B equal to 0. It's a good practice to initialize it and then wait for some time. It's a nanoseconds or picoseconds, the time units, 100 time units, and then add stimulus here. So this in the template generator, that when it would generate these part after this part automatically, that is give the module and the module name, also the it identifies the input and outputs, reg declaration and wire declaration, and it calls the or instantiate the module also, that is even done by the template generator, and initializing them also done by the template generator. So after this, the stimulus, we need to add this part. So that the user needs to add the stimulus part. This is #100 A01 A0 B1, and after 50 time units, A is 1 and B is 0. Similarly, the next combination of inputs 1 and 1 for A and B after 50 time units. So this is the stimulus, the end with this begin ends here. So you will see the space empty in the template generator, but in Vivado, Xilinx Vivado, you need to write the test bench as well. So previous versions of ISE had this template generator, which makes your job easy, that up to this portion that it is already given, and only stimulus part we need to add. Similarly, to monitor the output, we had this initial and $monitor. Within the quote, we see the same %D A B, and it can be B as well. So because it's a single bit, it can be B even, and YAB is given, and then N module. This is similar to the AND gate example, just the name of this gate is changed and then the OR gate is called over it. So the input, when we change it 00 A B, you can observe in the waveform editor, and 01 it would be 101, and then 11 it would give this 1 also. So the outputs in this case needs to be checked with the waveform editor. So then the half adder example of half adder and its test bench. We considered this half adder in the previous lectures. So the structural model of the half adder module and N module, which has two gates only, half adder module name, this is module name half adder, and the inputs A and B, output is sum and carry here. So you have the module XOR gate, if you just recall that XOR gate which has inputs A and B, and this is sum, and the output here, the carry is also a output. So what sum, its XOR function is given here. So this is the sum A XOR B, which is the comment. The gate name, sum is the output, A and B are the inputs. If we are instantiating in the instantiating the XOR gate, the component, and the carry also A B, that is an AND gate, and G2, this is named as G1 and G2, it's carry A and B. So as we said, this is the order doesn't matter. Also the data flow model, half adder, input A comma B, output sum or carry. So assign A XOR B, sum and carry A and B. So this is continuous assignment. Again, the order doesn't matter here. So the similar to instance statements, that assign statements, if you have multiple assign statements inside the module, and the order of continuous assign statement doesn't matter. So if the second statement needs the input, I mean the input is changing, and so the second statement, the last statement may be changing first, and then that needs to be updated in the first statement. It is very well done by the simulator. It's updated. So it's these are concurrent statements. Again, assign statements also of the concurrent, and these A and B, we call it as, if we compare it with the behavioral description, that is implicit sensitivity list, so which is right hand side of the equal to sign. So the sum is the variable which is assigned A and B. So the behavioral description of the off adder A, B, and the reg declaration needs to be noticed. Always at the rate A or B begin the sum A XOR B. So sum is assigned to the within the procedural code, or within the always block there is a procedural code which is having the multiple procedural codes. So the begin end comes in this. So A XOR B is sum and the A and B is carry. So the two statements here are executed sequentially. So it's not concurrent as in the case of the previous two models, the data flow and the structural description. So here the within the always block the statements are sequential. So here we need to take care of that order in which we are writing the code. So here it is first sum. This combination circuit doesn't have this that doesn't need that. So here we have given sum and carry. So XOR operation and the AND operation is specified because of the multiple statement. The begin block is used. Even the begin block in detail, we'll see how to name this for giving the code the clarity in the begin block. You can name them even these blocks also. So now taking this off adder, structural data flow and the behavioral model. So how do we write the test bench for it? Any one of the module can be considered. Here we have this test bench for the structural model. So module, it is simply called as test, half adder test, or you can add it any name here. And then the inputs AB, so which is declared as reg, and then output sum and carry are wires. You can see them. First inputs and outputs are declared, and then instantiate the UUT. So half adder UUT is the in module name which we have calling it here or instantiating here, which has this dot A, the input, here the local name A, dot B and B, and dot sum is sum, and dot carry is carry. So this is the instantiation of the module, half adder module. Similar to the AND gate, here you can see the half adder which is called or inside the test bench module. Next we give the stimulus to it. So the initialization would be better. Initial begin A 00, A and B are 00 here, 0, and wait for some time, 100 time units. So then comes the stimulus, add the stimulus. So initialization, first give the module name of the test bench, and then declare input and outputs, instantiate the module, initialize the inputs, and then add the stimulus. What are the combination of inputs we can have in the half adder? So after 50 time units, A 00 becomes 01. So this can be specified as, we have seen that A is equal to 1, B equal to 1. So we can explicitly specify this 1 bit 0, that is binary, B is 1 bit 1 also can be used. So hash 50 A 1 bit 101, now it is changed to 10, and in the other case it is 1 1. There are two inputs, so these are the possible combinations of input, the add stimulus, and end, because the multiple statements in the stimulus, which with the initialization, along with the initialization, that begin block ends here. And next, how to monitor this output in the waveform editor. So the initial, the printing that output, $monitor added here, $time is also a keyword here. $time is a function that which prints the simulation time. So comma, within the quote here, a percentage b, the binary, you can notice this will be printed binary, the comma, a, b, sum and carry. This is in the order, so we have to give this order of variables also, a, b, sum and carry, with close the bracket and with semicolon. So $monitor, now we have added the $time also. Let us see that what is the output of this going to be. See the example in which this a is the in where it is showing 1 1. Okay, so it is changing, so it where the marker is, it is showing that one, or here sum and carry. So we have the 0 0 when it is, so this is 0 initially, so a, b are 0, sum is 0 and carry is 0 till this point, and here still a is 0 and b is asserted here. So 0 1, so the sum becomes 1 0 1, sum becomes 0 till this one point, and then here we have this a made 1 and this is 0 1 0, it is going to be 1, the sum is going to be 1, and here we have this 1 and 1. Okay, so we have this 0, carry is becoming 1, so half adder gives the carry 1, whereas 0 1 it is going to be 0 and 1 0 is also 0 1, this is sum, this is 0 1 is going to be 1 1 0 1 and 1 1 0, we have a carry, so the carry in this cases it is 0. So the time resolution is taken 1 picosecond. You can see that time 0 is plotted, the $time and colon gives the 0 time, a 0 b 0, sum 0 and carry 0. So this is this portion. Okay, so it is this portion, it continues till this point. So we have given the time units, 100 time units of global reset, and then after 50 time units we have changed this a to 0 and b to 1. So this is 150, so 0 this portion at 150, so this is 0 and 1 and the sum is 1 here, sorry for the slip, 1, and then carry was 0. So this is the second one, and the third, after 50 time units again we have changed this a equal to 1 and b equal to 0, so the sum is 1 and carry is 0. So this is 1 and 0 and sum 1 and carry 0. This is that point of 200. So you can see this, the marker just given 200 1 0, and 250, after 50 time units we have changed this b also to 1, because a is already 1 and b is made 1, so the sum is 0 in the half adder and then it generates a carry which is 1. So this is up to 0 and this is the time unit of 150, and then it goes to 200, and then here is 250. So the resolution is given 1 picosecond, and the time units which we are changing it is the nanoseconds, shown here was nanoseconds. So you can see the half adder function which is simulated and shown in the waveform editor. The next the example which we had considered already is the multiplexer, where multiplexer works this way. This is 2 to 1 mux. So in which you have the x1 as an input and x2 considering as a black box, 2 into 1. So this is a select line. So select line is 1 bit for 2 inputs. So this is f here. So s is 0, x1 in this case x is 0. If x is 0, then x1 will be passed, and s is 1, x2 will be passed. So The structural model is instantiating of the gates. We had already looked into this example of input x1 x2, select is S, output is F. So wires K, G, H needs to be declared. What are the wires for this example? And NOT gate is output is K and input is S. AND gate, this is G, K and x1, and another instantiation H, which is S and x2. R is F, G and H here. So now this module in the data flow, we have simply changed to with the assigned statements. So the input x1 and x2, input is S also, output F. So assign this F as S tilde, that is tilde of S and x1. So here this one tilde of S tilde is K here, this part is K and x1. So this is a function and in the assigned statement, and we have only one simple statement compared to the structural one, S and x2 and given H, this is giving H and this whole thing is giving G. So that is the R function applied on this G and H gives F. So assign F equal to this, the case of data flow. So in the structural and data flow models also have the, how do we use this in the case of behavioral description even. So one syntax which I would like to introduce, because we are dealing with a multiplexer here. So the ternary operator of Verilog is useful. So it has a unary operator, and then it has this two input operands also, or operators of arithmetic operator or logical operators as well, binary one, and then this is the ternary operator, which is here a logical expression, question mark, the true expression and the false expression. That is the that is the ternary operator syntax. So this is used in conditional manner. So the like conditional statements, if this logical expression is true, assign this, get this true expression to where we need to assign it, otherwise false expression can be assigned to the variable. Now if we consider this, for example, x is true, take y, if x is false, take z. So very much suitable for the multiplexer example, in which the select input is 0, select the one input, or select input is 1, select the other input. So in that case, so considering a logical expression here at the first place. So here is A greater than B. This logic, A greater than B logic, is true if A is greater than B. This is just an example. Assign A itself to the variable where where we are using this. Otherwise, assign B. So this is an example again. So now considering this, we can have the nested conditions as well. So in using the ternary operator, which simplifies the code of the multiplexer, especially in multiplexer we use the select one. Now you can, I just give you the whole thing, that's better. So select one, if select is equal to 1, logical operator, if this is equal to 1, it is the option of 1 variable is chosen. If select is not equal to 1, then within it looks for the bracket, the false expression, where in the false expression we have the select 2 question mark op 2, and then within this it goes on in the nest. So if this is for select 1 is false, then go to select 2 and check whether select 2 is true. If select 2 is true, up to this point op 2 is going. If select 2 is false, then again check this select 3, and if select 3 is true, then go to op 3, assign the value op 3. If select 3 is false, and then check for select 4 whether it is that is equal to 4 or not, and then if it is true, op 4. If nothing is true and the select 1 is not, so go to select 2, select 2 is not, go to select 3, and select 3 is not, and select 4, select 4 is not, then go to the and assign this 8-bit xxx. So the select value, I am saying select 1 2 3 is just named here 1 2 3 4. So the select line can be 1 or 2 or 3 or 4. So in that case, if any of this it does not satisfy, it goes into the next ternary operator, 2, 3 and 4 and so on. So finally, if nothing is satisfied here, the logical expression, then assign this 8-bit binary XXX, that is unknown. X the expression is unknown. So this way, mostly in the multiplexes, the ternary operator is very much useful. So in our case, if we take this, we take the example again, we'll use this ternary operator also. So in the it's a behavioral model. So before that module, n module, the multiplexer x1, x2, sf. So input is xn, x f, output is f, and the reg declaration is required because we are using the always block x1 or x2 or s. It is good to have all the inputs in the sensitivity list x1, x2 and s. So if s is 0, f equal to x1, f is 0, f is x1. This is an if else statement. If else, if s is not 0, f is x2. So in the same way, so in the ternary operator we can say that yes question mark, that is if it is true, then select x2, if it is false, it is x1. Okay. So this needs to be the code for the, so you can use the assign statement in the data flow, something that is f here. This is f. So f, check the select line, if it's 1, this AND gate will be passing the value h, and this will be stopped, so that this becomes 0. So this does not give anything. So the x2 value will be passed to f. So f will be assigned x2. If this is not true, that is 0, then if it is 0, this becomes 1. So x1 line, the x1 value will be assigned to f. So the single assign statement using the ternary operator can give the simplified code of the that is, this is a data flow model. Of course, this is a data flow model, and usage of ternary operator is making use it in the conditional statements like this. So the test bench for the multiplexer. So how we are going to write the test bench for it, and the module of the multiplexer, module name mux test, and the reg, the inputs x1, x2 and s, wire is f, that is the output. We define the input and outputs and then instantiate the multiplexer. So instantiation of the multiplexer, the name of the module, Verilog module we had, unit under test, that x1 is x1, this is local expression, and dot x1 is the port name, and again the dot x2 from that port name and the local expression, and this is dot s select line, and dot f is the output and it output. So you can see the order which we had used it in the Verilog model. Anyway, the order doesn't matter, you can interchange as well. So this is the instantiation of that. Initial begin with so I would like to give the display, and then because this is also initial statement and the stimulus also an initial statement. So we can add it, we can even have it in the first way. Initial begin, we have the dollar display to display the x1, x2, s, and this line just to separate it, this will appear in the display in the console, and f. So this is within the code. So there is a dollar display, just displays what are the value, what is given in the string. Okay, so and then a dollar monitor here within the code we have x1, also x2 assigned, and s and f. Okay, so which are binary, and we have just shown for the clarity, if this line is added, we will see in the output the dollar display and dollar monitor add all combination of inputs. Here I have not initialized this 0 0, it is also possible to initialize it. So we have put all of them in the test combinations. So here x1 is not as a separate initialization. So here is the initial begin, x1 equal to 0, x2 is 0, s is 0, and give hash 10. So 10 time units, hash 10. After that, change the input x1 0, x2 1 and s 0. Hash 10 give some time, to reflect it in the output. To observe this, what is the time in this time duration, what would be the, so that is 0 1 1 0 for all select lines 0, 1 1 for select line 0. So these are all select line 0, what a change in x1 and x2 values. Similarly, we can make this for select 1 for 0 0 combinations 0 1 and then 1 0 with that select 1. Here this is select 1 for this continuation. Also x1 and x2 are 1 1, x1 and 10. So these are the combination of all combination of inputs when the select is 0 and select is 1 also. Okay, so this is a exhaustive testing we need to do for all the for the module which is generated. Here, if we see the output of it, the we had given dollar finish after this time units. It is the dollar finish is I am introducing in this test bench dollar display, dollar monitor, dollar finish. The dollar finish ends whenever that last statement is done. The time after that time unit, it completes the code execution and then end. So the initial where the begin is end. All the test cases as well as, so we have just pushed that display and dollar monitor to first and then given the all the test combinations. So now if we see the output of this, what would be the output? Now we have to see the multiplexer outputs which is given over here. So x initially it is 0 0 and select is also 0, and if select is 0, what is the x1, it is passing here, this x1 or x2, so x2 is passed here. So this is f which is passing this x2. Okay, this is also 0 0 0 0 after 10 time units. So this x2 is made 1, x2 is made 1 and x1 is 0 0 and this is 1. So select is still the 0. So this 0 which is selecting the select is 0 and this x2 is made 1. So we have x1 equal to 0 here and 1, and what is passed over here is still it is 0. So this x1 is till this point the select is 0 and this is made 1 here, this is 0, and at when we make this select 1, so this is the combination of the inverted ones can be checked over here, the x2, and here is 0 0 and this is also 0 0 and here also 0 0, and the change in 1 and 2 can be checked over here. This is 1 all over 1 and here 1 1. Okay, so the select is made 1 here, so you can see, and the changes in select 1 which is selecting the 0 here all over this point. Okay, so multiple changes can be done over in this point also. So depends on the select 0 0 0 1 1 0 combinations, 0 0 0 1 and then 1 0 1 1 all combinations. Here also 0 0 0 0 0 1 0 1, just to check the functionality here of the circuit. So we have this select line 0 completely for this time and it is 1 for this combination. Okay, so you can see the changes in this x1 and x2 changing between this two 0 and 1 combinations here. Okay, change in that. Okay, so the complete test bench gives the output which needs to be tested for all the cases. What if what is the select line gives you? It is a 1-bit 1. So where you make it 0 for all the time or make it 1 for all the time. So it should be giving the particular input. We can see this this x1 during this portion. Okay, and during this portion. Okay, during this portion we have to look into these details. So they completely, when s is 0, the whole x1 is passed. So x1 is passed. Okay, so the whole x1 is passed. You can see the x1 and which is coming over here directly for this portion, and then the whole of this x2 which is over here, this x2, when select is 1, so the all of this x2 it's coming to f. Okay, so we can say when s is 0, x1 is passed to f. When s is equal to 1, this f is assigned with x2. Okay, so here we saw that because both are 0, this could be, this is simply the 0 initial portion of this 10 time units. Okay, so we can still the select line is valid, s is 0 only, and the assert made it at this point with this. So we can consider from the 10 nanoseconds shown over here, whatever the select line was up to this complete x1 is transferred to f, and at this point at 40 time units, select line is 1. So x2 is passed over here, all the values of x2 you can see, and it is stopped with, so the changes are stopped with 70, and then it would go to that point. I think the if it is, the plot is cropped over here. So completely at 80 nanoseconds, that dollar finish, if you recall that in the test bench we put after the test conditions dollar finish, though that is at 80 nanoseconds. So after 10 time units up to 70, after 10 time units the dollar finish is called. So it finishes at 80 nanoseconds over here. Okay, so the x1, x2, s and f. So as we printed x1 in the monitor, x2, s, and there is a line we put also f, the output. So the combinations 0 0 x1 0 0 x2 and x1 x2 0 1 1 0 1 1 for the select lines 0, this is select line, and here x1 x2 0 0 0 1 1 0 1 1 for select line 1. So the select line 0, we get all the x1 values in this case, so which is same as this value, and when select is 1, this is the x2 values are passed over here. Okay, so before this change 0 0, so it is just the 0 0, it is just initialized values. These are just initialized values, either it can be from here or here. These are initialized values. This doesn't come into picture. Okay, so that's why we allow the global reset to maintain for some time, and then we try to change the values after 10 nanoseconds. We have this. Still this, if we configure that s equal to 0 is since s equal to 0, we take this 0 values from x1 here. So we follow the multiplexer outputs from select line 0 or 1. Okay, so this waveform editor gives you the picture of single bit input, how it is passed to the output. So the multiplexer can be of multi-bit input also. In that case, you have to expand this x1 and x2. X1 and x2 can be 4-bit. Suppose it is 0 to 3. X2 also can be 0 to 3. In that case, f will be also be 0 to 3. So we need to see the waveform editor outputs bitwise. Is first bit, that is x1 0 and x1 1, x1 2 and x1 3. Here 0 1 2 3, there are 4 bits, and x2 similarly 0, x2 1 and x2 2, and that is x2 3, 4 bits. If it is 4 bits and then 4 bits again, so the f will be 4 bits. So we have to view this each bit separately like this in the waveform editor. So passing x1 and x2 depends on the select line is given over here. So similarly for the full adder, a module and n module. So the full adder module had given already a, b, in, c in, output sum and c out. This is a data flow model anyway. This A XOR B XOR C in, C out is A and B, B and C in, C in and A. So the test bench for it, module full adder test bench, inputs reg A B C in are inputs to that, output is sum and C out. So a full adder is called over here, or the instantiated dot A dot B dot C in dot sum dot C out. So the port names and the expressions. This is the instantiation completed, and the will give initialize the inputs, or you can directly give the test combinations as well. So all of them are given 0, wait for 100 time units, initial time units, and then give the stimulus. The stimulus are 0 0 1, so given as B C in 0, all combinations of C in 0 and C in 1, A1 AB 1 1, C in 0, also the cases 1 1 and C in. So in these things, hash every input is changing with hash 50. Okay, that is 50 time units is given initially, and then so in the previous case we have given in the hash 50. After that change, after the hash 50 it exists. This is also similar, hash 50 at hash 50 this is changing, that's the meaning. In the previous example we took the change occurred and it retained after hash time units, then the next one is changing. So this is the difference you can notice. This is the stimulus combination. This combination can be generated instead of writing this all the combinations one by one. We can use the for loop also to generate all combination of inputs. We will see them in the coming classes. This is end in how monitoring the time. Okay, so A, B, C in, these are the inputs, and sum and C out. So the waveform editor, that is giving the outputs which is here as AB 0 0, and then this is 1, sum is 1, C out is 0 here. So 0 1 0 1, so we have 0, the carry is 0. So the input 0 0 and carry 1, the C in is 0, C in is 1, and it gives the sum, and here sum, and this is 1 0 1 1, and it's 0 and 1. So we have the carry generated in this case, C out. Okay, 0 0 1 and 1 0 0 1 0. So similarly 1 0, we have 1 here, and 1 1 0 0. The carry, you can see the carry generation whenever there is a 2 inputs, 1 1 1, this is also 1, the sum is 1, and carry is also 1 here. This is the combination. So the carry generation can be observed at these points. Okay, and the sum, this is sum 0 1, and here also this is only 1 and 1, and here it's sum 1, and this is 2 inputs 0 1, 2 inputs are 1 0 1 1. Here we have this 3 inputs 1, so sum is 1, and again the carry is 1. So it's a 1 bit adder, so that is a full adder here. So that is printed with time. So 0 time units, A0 B0 C in is 0, sum 0 C out is 0. Have the combination of AB 0 1, the sum 1, and C out 0. The combinations here AB C, sum 1 and C out. So because it have B is only 1 here, you have 2 inputs 1, so sum 0 carry generated, and 1, this is sum, and here similarly 2 inputs 1, the carry is generated, 2 inputs 1, carry is generated, and 2 input and 3 input, sum is 1 and carry out. So the combinations are covered. Also we can see the times at which the changes of inputs occurred. Okay, so 0 150, it is we are not able to see in the waveform editor, but 0 in the $time command used in the $monitor helps us to see the simulation time at which this is changed. So we have given first 100 time units of the global reset, and then 50 time units after 50 time 100 plus, so it's 150, first this is changed, and then another 50 time units, 50 time units, 50 time units, so this is changed over here. So this is about the full adder, testbench and its waveform editor output. So we have done the HDL design flow, we have the block diagram, and we have coded it, the design, and then it is the Verilog code. In the compilation or the simulation process, we have done it that using the test bench and then simulated. The functional verification is now done. That is, we have just verified it whether it's functionally correct. It's working as a full adder or half adder, AND gate, logic gate, or a multiplexer. That part, this is the front end part we are doing now. So that is up to this part. So we'll dig out further on the coding and the syntax of this Verilog and various digital circuit modeling. So 3 types of this modules generating the modules. Also we could see the multi-bit vector and other things, and different syntax parts of this Verilog also we'll be looking at in the coming lectures. So thank you.